Continuing our discussion of polynomials and their roots, let me continue looking at a function I mentioned in my last video, my previous video, and that is, let's look at the polynomial, the third degree polynomial, third order polynomial, p sub 3 of x equal to x cubed plus 9. Now, as I mentioned in class, that any polynomial where the highest power is an odd power must have at least one real root, okay? So we know this polynomial has one real root, and in fact it's pretty easy to calculate that that real root is x equal to negative the cube root of 9. Okay, how do we get that? It's quite easy, in that we set 0 equal to x cubed plus 9. Bring the 9 over to the other side of the equation, so we get negative 9 equal to x cubed, and then we take the cube root of both sides, and we get this solution right here. Okay, now let's look at the plot of that function from my graphing calculator. Here's a plot of that function. You see it has that classic sort of S shape. It goes flat here, comes back down. It crosses 0 at the point negative cube root of 9 right here. So it has one real root. Now, as we have mentioned about such polynomials, however, that we know that a third order polynomial can be factored. It can be factored into so as to have three roots. It has three factors. Actually, let me write that down. We know that P3 of Z, P3 of Z can be factored into something like this. Z minus Z1 times Z minus Z2 times Z minus Z3. Okay? Now, any complex roots that it has must occur in complex conjugate pairs. So I then factor this polynomial, the P3 sub 3 of Z equals Z cubed plus 9, and I factor it, and I find the three roots, Z1, Z2, and Z3, and these are the three roots here. Z1, Z2 are complex conjugates of one another, and then we have Z3, which is the same real root we had a moment ago. So these are the three roots for that polynomial. Right now I won't go into the details of how I factored the polynomial and found those roots, but it's not difficult, but we haven't covered everything we need to cover in order to know how to do that yet in our course. What I'm going to do, though, is on my grapher, I'm going to plot this function. Actually, what I'm going to do is I'm going to plot the magnitude of this function, okay, the magnitude of Z cubed plus 9, this thing right here. Because whenever this magnitude is equal to 0, the function will also equal 0. So plotting the magnitude of that function, here is what I get, okay? See that? We have, this is this axis right here. This is the x-axis. Okay, this axis along here is the y-axis, and I'm plotting this function here. I have x plus iy, so we have the x-axis and the y-axis cubed plus 9 magnitude, and I'm multiplying that by a 0.1 just to scale it down so it shows more details. So I have z equal to 0.1 times the magnitude of z cubed plus 9, because z is x plus iy. So here's what we see when we do that. Notice that we have, here's our real root. This is the real axis here. So we have our real root at negative cube root of 9. That's what this is. So, okay, and then we have are two complex conjugate roots located right here. They're on equal plus and minus sides here along the y-axis. Okay, but notice that they don't occur at y equals 0. They're not. If they occurred when y is equal to 0, then they would be plotted right here along the x-axis. So they're not real roots. They're complex conjugate roots. So we have one real root located right here at negative cube root of 9, and then we have our two complex conjugate roots right along there. So this is then the plot of that polynomial, but it's a plot as a complex valued function and not as just a function of the real variable x. And here you can see all the roots, positive and negative and so on. Notice, by the way, that if we do a slice, the x-axis is this axis right here. So we do a slice right along here, from here all the way up here. That is how the function looks along the x-axis. Here's the root. It's going negative, but even though it's going negative, the absolute value is starting to rise. So the function is going negative x, but the absolute value is getting larger. It flattens out in here somewhere, and then it continues to shoot up after that. So pretty interesting graph, and it illustrates how the roots of a polynomial appear.